Hi, everyone. I'm Anne-Marie Cody with the SETI Institute in Mountain View, California. I'm going to take some time in this video to tell you about the youngest stars across the sky and what we are learning about them with space telescopes such as TESS that can monitor their brightness over a range of time scales. The material that I'll present to you in this video contains contributions from Marvin Morgan, my former summer intern, who is now beginning as a graduate student at the University of Texas at Austin. So let's jump right in. What is a young star, otherwise known as a young stellar object, or YSO? You may have seen beautiful pictures of nebulae of dust and gas in our solar neighborhood. These are where young stars form. Many of them are born in young clusters or associations. And by young, we mean an object that is generally in the 1 to 10 million year age range. Now, there are low mass YSOs and higher mass YSOs. The lower mass ones you may have heard of are called T Tauri stars, and those typically have masses about that of the sun or lower and temperatures less than 7,000 degrees Kelvin. More specifically, the classical T Tauri stars still retain their the dust and gas from which they were born in the form of circumstellar disks, and they accrete gas from the inner circumstellar disk onto their surface. At higher mass, we have the Herbig AEBE stars, where E stands for emission line. Those emission lines are also produced by accretion, like the lower mass counterparts, the classical T Tauri stars. So many of these young stars have circumstellar disks, which they eventually disperse. Let me show you a schematic that you can keep in mind of a young star with a disk. We see the YSO in the center, and it may have a magnetic field. Here is a simple version of that shown in blue. The star is surrounded by a disk, which you can see in cutaway. The inner disk edge is where sublimation of dust begins at a temperature of about 1500 degrees Kelvin. Interior to that, it is too hot for the dust to exist, we believe, but you do have gas coming from the inner disk edge funneling onto the star via those magnetic field lines. Within this circumstellar disk, we think that planets may be forming, and therefore the end stages of star formation and the beginning of planet formation are intimately linked. You can see at left some of the processes which may be leading to planet formation in these types of disks. Now, we have reason to believe that the low and high mass YSOs may have fundamentally different accretion modes and magnetic field structures, as well as different inner disk radii, because as you probably know, the higher mass stars have much higher temperatures, so they can sublimate dust further out. This may have implications for how planets form in the regions closest into the star. So keep this schematic in mind as I show you what these stars, how they behave in the time domain. All of this material is in orbit around the central star. So you not only have gas plunging into the star, but if you have the appropriate view angle with your observation, you may also have dust obscuring the central star at times. And there could be spots on the star, which is itself rotating. All of these processes create the variability that you're going to see next. So here are a few key science areas that we're hoping to probe by observing young stars and their brightness variations. We'd like to understand the structure and dynamics of the circumstellar disk, since that is so important as the site of planet formation. We'd also like to understand how magnetic fields are generated in these objects and what their geometry is as a function of mass. That is also related to the accretion dynamics, how gas flows from the inner disk to the central star. Again, we'd like to see how that varies with mass and how that helps build up the central star in the end of its formation period. Stellar structure is something that we can access by studying eclipsing binary systems, for example, measuring mass and radius as a function of stellar age. And related, we'd like to know if there are substellar companions, and if so, at which stages are we able to observe them? Remember, these are very young stars, so there may not be fully formed planets around them yet, but there may be something observable in the act of formation. And finally, these are very dynamic systems. As you will see in a moment, the variability can be quite crazy, and it is an indication of the physical dynamics going on in these systems. We'd like to see how that varies as a function of time, basically how stable the processes are that create variability in young stars. So what have we learned from previous space telescopes prior to TESS? Those include observatories like Corot, which was a French mission, and the Kepler K2 mission, which together observed hundreds of mostly low mass young stars. So we're talking about the T Tauri stars here. What we found was variability on a wide variety of timescales, from minutes to months, which was the duration of the observations. They are variable on longer timescales as well. This variability tells us about the dynamics and geometry of young stars and their circumstellar environment. What we found previously for the low mass young stars is that we could classify the variability into different categories. And I show you an example of each here. There are 8 different categories, and for each you are seeing a light curve from a space telescope indicating that type of variability, as well as what we think the physical mechanism is driving that variability. So perhaps the most simple is the periodic or multi-periodic light curves, and we believe those are due to magnetic star spots on the stellar surface. Every time the star completes a rotation, you will see a repeat period of whatever the star spot pattern is, according to how large those dark spots are and how they are distributed about the stellar surface. So you tend to get roughly sinusoidal patterns from star spots. If you have multiple star spots that are potentially evolving or at different stellar latitudes, or if the star itself is pulsating, you may get multiple periods. We also see quasi-periodic behavior, which is a bit more difficult to interpret. It does also have a repeating pattern, but it tends to change in amplitude and shape from one cycle to the next. This may also be hot spots, but perhaps instead of cool magnetic spots, it could be accretion hot spots where the gas coming from the inner disk falls onto the stellar surface. Those might be more dynamic, and hence you would not have as stable a pattern. It could also be material in the inner disk occulting the star as it completes its orbit. We have another type of variability, which we refer to as bursting. And we believe this is due to unsteady accretion from the inner disk. So material is plunging in onto the stellar surface and causing brightening events. So bursters show not necessarily periodic, although they can be, brightening events, and the light curve tends to show these peaks, which you can see occurring throughout the time series. The opposite of burster is what we call a dipper, where instead of having brightening events, you see fading events. And some of those can be quasi-periodic, or sometimes they can be aperiodic. And this is probably telling us something about the location in the disk where occulting dust is located. And if we have the appropriate line of sight, that dust will pass between us and the star, causing it to fade at times. We also have a more stochastic light curves. These are somewhat similar to the bursters, but their flux does not show distinct brightening events. It is just kind of bouncing up and down. We think that is also due to accretion variations. And finally, there are some rarer light curves which just show long time scale undulations. It's not so clear what that is due to, but maybe some kind of disk modulation. So these are the 8 types of behaviors we saw for young low mass stars. Question is, do we see the same types of behaviors from high mass stars? And we will get to that briefly. First of all, though, before I do that, I want to show you how we assess these light curves statistically. And from Corot and Kepler, again, we found that we could apply 2 statistical measures, which I refer to as Q and M. Q measures how periodic a light curve is. So down here are examples of different light curves. The upper left is highly periodic, and that would have a Q of 0. So anything with a low Q value is has a very nicely repeating pattern. Anything with a Q value approaching 1 is basically stochastic, and there is no periodicity to be found, as seen at the upper right. In between, we have values of Q ranging from 0.15 to 0.7, 0.85, and those are what we would call the quasi-periodic behaviors, some examples of which you can see here, where there is a repeating pattern, but it's not perfectly repeating. So that is what this statistic called Q is. And I will show you why that's important in a moment, but first let's also take a look at what this other statistic M is. M is a measure of the flux symmetry in a light curve. So highly negative values of M are indicative of bursting behavior. So the burster stars, which typically have kind of a continuum level above which they display brightening events, would have very negative M values. And then if you flip the light curve, very positive M values are the dippers. So they have sort of a continuum level below which they display fading events. Now, if you have a more symmetric light curve, like a stochastic example, then you would get a value of 0. So why am I showing you these statistics? Well, it turns out that if we measure these statistics, which are described in my papers from 2014 and 2018, if you want to see the details, if you measure them for a large sample of young stars, and then you plot Q versus M, you basically get all these different categories of variability, which are here colored by eye, according to the by eye variability classification for a sample of low mass stars in the upper Scorpius region. So you can see in the legend here what all these different variability types are. And then you can see where on the diagram these variability types tend to fall. For example, the dipper stars, as I mentioned, have high positive values of M, so they're in the bottom part of this plot. And they are also quasi-periodic, so they have values of Q that aren't quite 0 because they're not perfectly periodic, but they're also not all the way going up to 1. So the quasi-periodic dippers are in the cyan color here. The bursters are at the top, and the quasi-periodic objects are in the middle in green. The periodic spotted objects show up as purple, and in the bottom left, which is obscured, you would have eclipsing binary systems, which have fading events that are very periodic. There don't happen to be any in this particular sample. So this is what we see for the young low mass stars. Now, what happens when we go to higher mass? So we've got the classical T-Tauri on the one hand, which I just told you about. They have inner disk edges that are approximately 1 astronomical unit from the central star, and there is a co-rotation period where that material is orbiting around the star at the same on the same time scale as its rotation period. That's typically around a few days. And there is often dust there around the inner disk edge, which is often right at the co-rotation radius. This is important because again, if we are looking at the appropriate line of sight to the star and appropriate view angle, then we will see dust at the inner disk edge occulting the central star, creating those dipper light curves. These objects also have significant magnetic fields, which again mediate the accretion and cause large magnetic cool spots on the stellar surface. So that's the low mass stars. What do we know about the high mass stars or the Herbigs? So they're also accreting, but we don't understand so much about the modes of accretion, the magnetic field structure, etc. The entire sample of Herbig stars is quite scattered across the sky, but individual stars reside again in clusters. These are hotter stars, and so the inner disk edge most likely lies further out because of dust sublimation. So it is hypothesized that there is little to no dust material at co-rotation, so you may not get the same fading events that we see in the low mass star dipper population. That is something that we wish to verify. Magnetic field generation in higher mass stars is a complicated topic, but we also have reason to believe that the magnetic fields are weaker or even non-existent. And that should again show up in the time series dynamics when we look at these stars and attain photometry, time series photometry on them. So on that note, what I have been doing is keeping in mind everything that we have learned about low mass stars from previous space telescopes is transitioning to the higher mass region with TESS. And this is a great thing to do because TESS, as you know, monitors bright stars. And the Herbig AE/BE stars are typically the brightest young stars in their respective clusters and associations. So I have mined the literature for Herbig A/B stars across the sky, checked which ones are observable with TESS, and we have a sample so far of several hundred with additional candidates on top of that. Now, this is not a perfect sample. It turns out, as we'll see, that some things that are not Herbig stars do sneak into it. So we are still in the process of vetting what stars are actually in there. But I went ahead and ran these objects, which were observed by TESS in its full frame image mode through my photometry pipeline. And to make a long story short, just like the low mass counterparts, virtually all Herbig stars are variable on some level, with behavior ranging from periodic, multi-periodic to stochastic type light curves. I will say that the light curve morphologies are a little more challenging to classify than the lower mass T-Tauri stars, which nicely fit into those 8 categories. So let's take a look at what TESS light curves of young stars in the high mass regime actually look like. And just to show you the differences before I do that of the sample selection for TESS versus previous space telescopes, we are looking primarily at spectral types of B, A, and F. Now, TESS does observe K and M stars, but they are much fainter and subject to crowding, so it's more difficult to obtain photometry for the low mass stars. It certainly is possible. I'm just not focusing on that here. For from the Kepler K2 mission, we obtained several hundred light curves for stars, primarily in the K and M range. So these are highly complementary samples. Let's take a look right off the bat before we check out the light curves of this at this Q and M diagram now for Herbig stars observed with TESS. As you can see, they display all different types of variability, from bursting on the top to dipping on the bottom to symmetric and quasi-periodic behaviors. We even have a bunch of eclipsing binaries which show up on the lower left. But what I want to highlight here is a bit of a gap when you're looking at moderate values of Q, so quasi-periodic behavior, and positive values of M. These are, again, where the dippers live. Are there quasi-periodic dippers among the Herbig stars? Because as you recall, I mentioned that we have reason to believe that there is not much dust at the co-rotation radius of these higher mass stars due to their higher temperatures and sublimation. So it would be a little bit surprising to find dippers here, but we do actually have objects in this regime. What are they? So this is very interesting. Turns out one of them is not a dipper at all. It's just some kind of interesting pulsator that happens to have a larger M value. One of them is a K or M spectral type star that snuck into the sample. So that is just like the stars we observed with Corot and Kepler K2. The remaining objects that we can classify as dippers are actually F stars. So that suggests that the dipper quasi-periodic dipping phenomenon stops after F spectral types. There is a single star, which you can see in cyan here. And by the way, the size of the points corresponds, is scaled according to the amplitude of the variability. It's actually to the 1/3 power, so it's not exactly linear, but you can see basically the bigger dots have the larger amplitudes. So V1012 Ori is an A star, and it shows dipping behavior in the TESS sample. It's the only Herbig AEB star that shows up as a quasi-periodic dipper. So that is really fascinating, and it does seem to confirm that there may be a lack of inner disk dust surrounding these stars, and therefore we don't see periodic occultation events. We do see dipping behavior or fading events on longer time scales, but it's mostly aperiodic, or perhaps it repeats on greater than 1 week or 1 month time scales. Here's an example of a Herbig star, VX-CAS, which you can see fading events, but they don't necessarily phase up at a particular period. So as I mentioned, there are only a small handful of quasi-periodic dippers. And this is the one special case of V1012 Ori. This is what its light curve looks like. So it's not at all perfectly periodic, but you do see this repeating pattern happening roughly every 5 or 6 days. And the rest of these examples, as I mentioned, are F stars, so slightly lower in mass than the Herbig stars. So the quasi-periodic dippers make up only a couple % of our entire sample, whereas they were more like 20% of the low mass stars observed by previous space telescopes. What we see a lot of is stochastic behavior. So here are a couple examples where the brightness as a function of time is essentially just bouncing around. We think the time scales of this bouncing and the amplitudes encode information about the gas accretion from that inner disk. We do see a few of these objects that we refer to as bursters, where they're again stochastic, but they tend to favor brightening events. But as you can see, this is normalized flux as a function of time. The brightening events are only of order 1 to a few %, whereas the amplitudes in some cases for the low mass stars were much higher. So this is again probably telling us something about the differences in accretion mode between the high mass stars observed by TESS and the lower mass KM stars. And I do want to circle back to this question of magnetic fields at higher mass. It has been proposed that magnetic field generation is much different than for low mass stars, and that magnetic fields should be weak or absent at higher mass stars. And we can check that by looking for spot modulation as indicated by periodic or quasi-periodic light curves in the higher mass stars. And periodic variability is often an indication of a spotted surface, although we have to be careful to distinguish it from stellar pulsation. Here are two examples to show that we are indeed seeing periodic behavior in Herbig stars. And so that is an indication that there are, in fact, magnetic fields in these objects driving surface spots. And that has been studied a little bit previously with the Corot mission. You can refer to this paper by Fossati et al. To see some further examples, and we're starting to expand on that. And finally, we'd like to take a look at the evolution of time variability. Many of the light curves are observed in multiple TESS sectors, many of the stars, excuse me, and we do see changes in the nature of the variability. Here's one example here. We do need to be careful to distinguish intrinsic astrophysical changes from systematics to do with the data taking. So in this case, you can see a change in amplitude of the star, but suspiciously it happens after the mid-sector gap. So whether that's real or not is not entirely clear here, but we can at least look at the shape of the variability and detect changes on timescales of months or even years, depending on how often a particular star was observed with TESS. This will tell us about the stability of the physical processes generating the variability in these stars. We find many eclipsing systems, which I won't go into too much, but can provide measurements of mass and radii for these stars, which can then be compared with young star evolution models. We're searching for substellar companions, which are very hard to find given all the variability that is happening, and also the potential confusion with eclipsing systems. We do have light curves where there are interesting percent or so level dips, and we are following them up to figure out what the origin of those dips are, whether they could be a planet or just a blended eclipsing binary system. So on that note, I'll leave you with a few caveats. Even though these stars are quite bright, there are still crowding issues due to the large 21 arcsecond pixels of TESS. Here's an example of a Herbig star within a fairly crowded young star environment. And when we want to go look at that star, which is shown at left in a ground-based image, we obtain the TESS full frame image, and we see that it is it's getting blended with the two brighter neighboring stars. Fortunately for us, the Herbig stars are usually fairly isolated. For example, like this one at the upper left could be a Herbig star. So they tend to dominate the variability in the light curve. Another caveat, though, is that the literature compilations of Herbig A/B stars I'm finding tend to include more evolved stars. So the classical BE stars, for example, have dust surrounding them, but it is not primordial circumstellar dust. It has been expelled by the star in later evolutionary stages. Many of those exhibit stellar pulsations. So here's an example of a light curve of a BE star. That is probably not surface star spots creating the variability. So we have to be careful to actually clean the list for these interlopers, shall we say. Okay, so moving forward, there are some issues with the light curves to do with scattered light. I didn't show you examples of that, but we're in the process of comparing different pipelines which may include these Herbig stars to select the best version for each object in the sample. And eventually we hope to integrate ground-based data and make connections to other observational methods such as spectral polarimetry and interferometry, which are possible thanks to the very bright nature of these high mass young stars. So I'll leave you with a few takeaway points. As you have seen, TESS has observed hundreds of young high mass stars over the past few years. We see widespread variability over a large range of timescales and amplitudes. I would say over even larger range than for the young low mass stars. We do see a little bit of quasi-periodic dipper behavior, but it's much more rare at high mass and mainly confined to the F stars. This could be a confirmation that the inner disk radii, at least the dusty part of the disk, is larger around these high mass stars. And finally, we see a lot of periodic or quasi-periodic behavior suggested of magnetic star spots present on the surface of these objects. And that confirms that there are, in fact, magnetic fields on even high mass stars, which was for a while not expected. So that was a bit of a summary. As you can see, there is much to do in continuing to explore the high mass stars observed by TESS and to follow up on them. And I'm excited to see what the full comparison with the lower mass young stars reveals.